Good evening. I wanted to make a quick video on demonstrating how to directly derive the moment generating function, specifically for a normal distribution in this case. Usually when I see derivations of the moment generating function for the normal distribution in particular, there's usually some tricks that are involved, but I wanted to showcase how to directly compute or directly derive the MGF for a normal distribution without any fancy tricks or any fancy stuff. So just to quickly cover what exactly a moment generating function is basically a function that characterizes the so-called moments of a distribution, and each MGF is uniquely defined in the sense that if two different random variables have the same moment generating function, then they have the exact same distribution. And I've also listed three use cases for the MGF. The most common is the first one, which allows you to compute moments by taking derivatives. And so, for example, if I wanted to compute the first or second or third, so on moment, that I can just take first, second, third derivatives of the MGF and evaluate them at 0. Another common use case is in the algebra of random variables. And so, for example, the sum of two or more random variables has an MGF that's equal to the product of those individual MGFs. And lastly, this is probably a lesser known use case, but you can use an MGF to derive the probability density function of a random variable using an inverse Laplace transform, or maybe it was inverse Fourier. I don't remember which one exactly. I don't use this very often, so to speak, but it is definitely possible. You actually take the inverse of the characteristic function, not the moment generating function. But if you're interested, you can look this up further for yourself. So the main tool, so to speak, that I'll be using to actually do this computation is by utilizing a Gaussian integral. And in one of its general forms, a Gaussian integral takes on the form from negative infinity to positive infinity of an exponent raised to a 2-degree polynomial. So we have e to the negative ax squared plus bx plus c, and this evaluates to root pi over a e to the b squared over 4a plus c. And these are extremely useful when dealing with normal distributions in particular, because a normal distribution essentially takes on this exact form. So I'll be taking advantage of this when we derive the MGF. So now that we've got all that fun stuff out of the way, we can actually get started. So here we have x as a normally distributed random variable with mean mu and variance sigma squared. I'll be deriving the general case, and so these can be pretty much arbitrary values almost. And our goal is to find the MGF denoted by m of t. So first we'll note the PDF of x is 1 over root 2 pi sigma e to the negative 1 over 2 sigma squared x minus mu squared. And by the definition of moment generating functions, this is just the expected value of e to the tx. And by Lotus, or law of the unconscious statistician, as you should know from elementary statistics, to actually compute this expected value, we just multiply e to the tx by the PDF of x. And so that gives us this nasty looking integral, but I promise it's not as difficult as it looks. So now I've rewritten this expected value for reference. This is essentially what we will be working with from here on out. And I'll begin by expanding this x minus mu squared term here. So when we expand it, we get x squared minus 2x mu plus mu squared. And so now that gives us this expansion here. And notice that I've distributed this negative here. So here we have negative 1 over 2 sigma squared. I'm just distributing this negative across these terms. And so this becomes negative x squared plus 2x mu minus mu squared. So make sure you don't forget that. And by the exponential rules, since we have two exponents multiplying each other, we can add them by rules of exponents. And so here I've added this plus tx at the end to replace that multiplication. And I want this tx to have the same denominator. I want everything on essentially the same playing field. And so we can multiply this by 1 and this by 2 sigma squared. Obviously multiplying this by 1 doesn't do anything, but now we have tx 2 sigma squared. So you can see down here I have my tx term, and it has the coefficient, extra coefficient 2 sigma squared. That way we can put everything all on the same denominator. And one last simplification we can make is to factor out this x term. And so you can see here, if I factor out this x, we are left with 2 mu plus 2 sigma squared t. Alright, so now up at the top, this is essentially what we just derived from the last slide. There's just a couple other simplifications, and then we can compute the Gaussian integral. And so one thing we can do is distribute this 2 sigma squared denominator. And so now I'll be separating these three terms by just distributing the denominator. And so here we have negative x squared over 2 sigma squared plus, and then this 2 and 2 cancels out, so I have mu over sigma squared, and then this 2 sigma squared cancels out completely, leaving me with just t. And so my x term reduces to mu over sigma squared plus t, and then we have minus mu squared over 2 sigma squared. So that one is pretty straightforward. And notice that this last term here, mu squared over 2 sigma squared, does not depend on x whatsoever, and so we can completely take it out of the integral since it's a constant. And so now we are left with this integral here. And notice that this takes on the form of a Gaussian integral, e to the negative ax squared plus bx plus c, where in this case c is 0. We can also have this term here be c, but it's needlessly complicated, so we could just take it out of the integral. And getting the values for the Gaussian integral, which you can see for reference here, our a term is 1 over 2 sigma squared, because remember it is e to the negative a x squared, and we have negative 1 over 2 sigma squared, so a is positive 1 over 2 sigma squared. 1 over 4a is sigma squared over 2, which we will use to divide b squared. B is our coefficient here, mu over sigma squared plus t, and then we can square this term to get this lovely expression here. And then finally dividing this b squared by our 4a, which is essentially multiplying by sigma squared and dividing by 2, we get this expression here. And so now our final integral, or evaluating this integral here, my mouse went off the screen, we get pi over a, which is root 2 pi sigma, and then e raised to this whole expression here. So e over mu squared over 2 sigma squared plus mu t plus sigma squared t squared plus 2. So this is basically what we had in the previous slide, and we just computed the Gaussian integral. And so now we have this constant term multiplied by this Gaussian integral, which we just evaluated. And then you can see immediately that this root 2 sigma squared cancels out. We have this negative mu squared over 2 sigma squared term and the positive mu squared over 2 sigma squared term. So that cancels out as well. And then we are finally left with e to the mu t plus sigma squared t squared over 2, which is precisely the moment generating function of a normal distribution. So hopefully you were able to follow along, and hopefully that makes sense. This is how you can directly compute the MGF without using any fancy tricks, besides a Gaussian integral, of course. So yeah, hopefully that helps, and thanks for watching.